Hey there, Code Conquerors! Welcome back to our digital dojo on Conquering the JavaScript Interview. Today we're going to crack a classic but tricky question. Is a number a power of 2? Like the thumbnail and the title of this video imply. It's like a secret handshake in the binary world, and we're going to unravel this mystery together. But first, if you're interested, check the description down below for a link to our community membership, where you can dive into an ocean of coding knowledge. For just $25 a month, you get over 300 hours of our in-depth tutorials, walkthroughs, lectures, labs, etc., our entire full-stack program, and my comprehensive React course, plus any new courses or course updates or content I continually put out into our available content. They're automatically yours, free, no extra charge on you whatsoever. So with Covalence, you're not just learning, you're joining a thriving community of coders who never stop evolving. So let's get our Bitwise gloves on like we have in the past couple videos, and we're going to make to see if our number can make the cut and be a power of 2. So the problem here is very straightforward. We just need to write a function, is power of 2, that can take a number input, and its entire job is just to sniff out if a number is a power of 2. An exclusive club of like 2, 4, 8, 16. So basically, just like the prompt has right there, can it be 2 to the power of x? If that rule checks out, then you're pretty much good to go. This is a great beginner interview question that can be solved without bitwise operators fairly easily with a little bit of math knowledge and trickery, but it's even cooler if you can solve it with a bitwise operator, which is why I want to show y'all how to use it here. And I think the diagram.png in my VS Code window there is a dead giveaway of which bitwise operator we're going to be using today. So it's pretty easy. The catch is to remember that a number to the power of 2 cannot be 0 or negative, so we're going to be throwing out those numbers. There are edge cases where we can mess with shift operators to catch that and go for and make it work, but we're not going to focus on that for now. So yeah, powers of 2, positive, greater than 0, so we're going to make our function with an easy if statement to catch that. It's going to simply output a Boolean answer of either true or false. It's going to be fairly straightforward for the output it needs to return. And all we really need to do is, we're going to be using a clever little trick to get this to work. And I'll tell y'all what that is after I actually code it out, and you'll see how simple it is. And then we're going to write some comments like I always do that show us how the binary arithmetic works, and then we'll get it done. So yeah. And I'll also show a non-bitwise way to do it, since it is also fairly straightforward. So yeah, here we go. Let's jump on into this one pretty quickly today. It's not too terribly complicated as long as you know what the trick is. So in is power of 2, like I said, first thing we're going to be doing is making sure our input, a little sanitization, if you will. We're going to be making sure our number input is greater than or equal to, if it's less than or equal to 0, not greater than, if it's less than or equal to 0, we're going to automatically return false, early return, because there's no need to check to see if it's power of 2. Remember, they have to be positive integers that are non-zero. So if it is negative or if it is 0, we're going to go ahead and just return a false on that one. Like I said, there's ways to get around this with shift and things like, one of the shift operators and things like that. But for now, we're simply going to do our return statement for our Boolean comparison. So we're going to have to do something, and we're going to compare it to 0 with the trick that I will describe how it works here in a moment. So again, like I wouldn't expect you to know this if you were a beginner coming in and you had even just learned about these bitwise operators. Again, you can always grab this prompt and the code and the CodePen, and I do recommend you follow along with me where possible to at least build the muscle memory of how these operators work and how to begin thinking about it. So this is one of those very much like preparation meets opportunities means good luck type scenarios, where if you've watched this video, you go to an interview, you get a question, you're like, oh, I've seen this before, or this utilizes power of 2 to solve something bigger. I know how to do this in a really cool way. So what is the trick with the question marks that we're going to replace here? Well, we need to do some kind of operation. We know it's going to be using the AND gate here. As a quick reminder, the AND takes 2 digits, 2 binary digits specifically, and it gives back 1 only if both are 1. In our example of our friends bit and byte, it is a very exclusive club security guard that only allows bit and byte in if they both have VIP passes. This is not the lax one. This is the strict bouncer in our analogy. which again, you can find in previous videos where I break down each operator with a specific algorithm in those videos, and this one's just something I wanted to throw out. So, yeah, all zeros gets us a 0. 0 and 1 is a 0. It's commutative, meaning if it's reversed to 1 and 0, it doesn't really matter. It's going to be the same thing. It's still a 0. And if it's a 1 and a 1, well, then we get a 1. So that's the only case we're going to get a 1 here. And this knowledge right here, this trick, along with a quick bit mask trick we're going to be doing, is how we're going to solve this entire thing with one bitwise operator. So we are going to be doing the following. We're going to do an AND bitwise operation with the number against its own -1 mask, and believe it or not, that is all that needs to be done to get this solved. So let's do our quick check here of like, is power of 2 16? So let's go ahead and do this. We're going to do is power of 2 16, should be true. And then 1 should be true, and then 18 should be false. So let's see, 1 is true, and then 18 is indeed false. So we've already passed the tests. It's all fairly straightforward here, as you can see. So yeah, what is the trick here, and how does it work? How do we utilize bitwise operations in this to make this super cool thing? So the strategy is that powers of 2 have a unique trait in the binary world. They are like a singular dancer on a stage of zeros. So in binary, a power of 2 is represented by a 1 followed by all zeros. For example, 4 is 100 in binary. 4 is a power of 2. 8 is a power of 2, and 8 is 1,000, and so on and so forth. So the bitwise trick here is pretty clever, and again, it's a trick. It's one of those things where if you have binary math experience, maybe from a computer science background in university or something like that, then you probably know some of these things. But if you're coming here as a beginner, especially as like a web developer, there's no way you're going to know this. But nevertheless, now you do. So here's the clever trick, is that when you take a power of 2 and subtract 1 from it, the result is a sequence of 1s to the right of where there were zeros. So if we bitwise and our original number with the subtracted 1 number, we should totally get zeros down the line. It's like checking, is basically making sure that the power of 2 mask works, and that's all the check does. Meaning, let's go down to 8, something I know off the top of my head, which is 1,000. So we have our input number converted to binary. It passes the check of being greater than or equal to 0. In terms of the early return, rather. It's not less than or equal to 0, I should say. So it passes that test. Then we take the number, and then we're going to look at the number, subtract 1. So if that's 1,000, and we're going to subtract 1 to get 7, that is represented by that in binary right there. So that is what our binary little mask here looks like. That's number minus 1. Let's go ahead and AND these suckers together. I'm going to do it this way this time. I like that. So there's our AND operation for each column of our binary. A little bit different than the previous videos I've done. So that is our AND for each column, which gives us a 1 and a 0, give us a 0. 1 and a 0 and 1, 0 and 1, 0 and 1, they're all zeros. Remember, the only time you get 1 is if both columns are 1. That's the only way it could work. So the binary representation of a bunch of zeros is zeros. Does that strict comparison equal to 0? It does, and hence why we get true as our output. Because the left-hand operation right here in the return statement generates this binary 0, which converts to the integer 0, right? Converts to integer 0, and that does a strict comparison of type and value on this number 0, which is true. Therefore, that's why we get true on the power of 8. Now, let's confirm that if we switch it to 9, we get false. Let's deep dive how this 9 works and take a look at it. So, knowing what we know now, let's go ahead and remove that. I'll leave that part in. 9 is 1001. 1001 would be the binary representation of 9. So if we subtract 1 from it, we get 1000. And then what we have to do from there is simply do the same thing. In our AND comparison, we're going to look at the left-hand column. That's going to be a 1. That's our AND operator working as expected. The fact you already have a non-zero tells us that we have a problem. 0, 0, 0. Okay, so that is the binary representation of the value 8, like we just saw a moment ago, and that definitely does not equal 0, so that is why we end up with that comparison. saying, nope, that is a false, and that does not work out the way we expect it to. So again, this is a clever little trick so that so long as you know what the that binary powers of 2s are always going to be 1s with a bunch of zeros after them, and you subtract 1 from it, do the AND operator, and as long as the bits all wind up in zeros, meaning it's commutative, so as long as one of the parts of the columns always has a 0, it'll zero out, and boom, you're good to go. So that is the whole trick behind this and how it works. And again, it's one of those things that, there you go. You now have this in your back pocket. Please come back and comment on these videos or any videos if you hit an interview and you encounter one of these questions and it gives you a leg up in that interview. And again, that may not mean that I aced it 100% and I explained it or I made a joke out of it like I tend to or something like that. It could just mean that, hey, it was a reminder of how I did something, or it served as a talking point during the interview. It doesn't have to necessarily mean you solved it exactly like I did, explained it like I did, or something like that. It could even mean like, I remember seeing this, so at least it gave me a leg up of where to go. All right. Yeah, so I don't think I've done 16 in binary. So I paused a moment ago to bring up a binary calculator to make sure I don't make a fool of myself. But if I do like, what is the binary of 16? That would be 10,000, right? So that would, if that was 8, that means 16 would have to be that, logically. Yeah, and if we did the minus 1 of that, then that would be simply 0 and a bunch of 1s after it, because that's the conversion. And then you would do column, and then because of non-commutative, you already know that these, with AND operation, it's all going to be zeros, which is the binary integer version or decimal version of 0. Does that compare to 0? And it's true. So if we save this, we get true, because is power of 16 true? It is true, because, well, that's what we know it is right there, right? So there you go. I think that's a pretty cool trick to know about binary powers of 2 are going to be 1s and a bunch of zeros following it. So that's the big TLDR of the video. Powers of 2 in binary are represented by 1 and a bunch of zeros. So if you know that, you can do some cool tricks along with it. All right. Yeah, so let's see. What else we actually want to do? Oh, yeah. So I guess we should actually show how this looks from a non-bitwise approach. So again, uses a little arithmetic magic. You'll actually see this more on Stack Overflow and places like that. Again, like bitwise is kind of like just going super fancy if you know about it. If you don't, it's typically less legible. And, again, you have to do a lot of deep diving to figure out an answer someone gives you if it's with bitwise and you're not familiar with it. So an alternate way to do it is without bitwise operators, obviously. We're going to have to do something with a loop. Basically, we're going to take our input number and simply continually divide it by 2 inside of a loop until it goes down to 1. And at each step of the way, if the number is still divisible by 2, we are good to go. But if at any step the number is not divisible by 2, meaning a remainder that is not 0, it returns false. And that's it. So basically, keep dividing a number by 2 and keep checking to make sure that number is divisible evenly by 2, because if it's not, then we no longer have a power of 2. So basically, it's going to be the same check. So let's go ahead and write our second version of it here, which is function is power of 2 non-bitwise. Okay, it's going to have the same input, which is number. We're going to run the same check. Is it less than or equal to 0? Because if that's the case, we don't have a power of 2, so we're going to return early. Now, we're going to be running an indeterminate number of iterations here, so a good use case for that will be the while loop compared to a for loop. So long as the number doesn't equals 1, we're going to keep on dividing it down until it does get to 1. So we're going to do divide equals 2. Now, I got to say, I feel like that's an operation I don't write all that often, divide equals. I don't know. Y'all get in the comments if you've had other algorithms or solutions to just any coding problem you've had where you've done a divide equals. I feel like I don't do that one all that often. Remember, because that's just num equals num divide by 2 is what this shorthand is right. Here's what we're looking at, right? That's what the shorthand is for that right there. But yeah, I feel like I don't write that one all that often, so it's kind of weird to look at when I wrote it earlier. So if number is modulus 2, our even check. If it is not an even number as we iterate over by dividing by 2 on each one, then it can't be a power of 2 and we return false. If it doesn't get caught by the early return, If it makes it all the way through the loop down to 1, that means we have a power of 2, and we got it right here. So let's go ahead and do our check, which was is power of 2 non-bitwise. We know 16 was one of them. It still gets true. 17 is not one of them. We get false. So there we go. It works the exact same way. And, I would definitely argue that if you know a little bit of math background, this is much easier to figure out with this trick than the bitwise one. But the bitwise one will give you a lot more to discuss, gives you the better fundamental knowledge of JavaScript and how it interacts with low-level stuff on the computer, aka binary. A bit more binary tricks in your playbook that you could utilize. And again, if this comes up in an interview and you can solve it with a bitwise, you will look stellar, let me tell you. So, our normal TLDR, remember your Christmas lights analogy, and lights light up only if both strings agree to shine a bulb, or either one has to have a bulb on, right? More the merrier. Not will flip every bulb if it's on. If it goes off, if it's off, it lights up. Zor, aka the fun one I started with in this Bitwise Basics series, only lights up unique bulbs from each string. It's a solo partier, and shift slides the bulbs left to the right either way. That's what happens there. So remember your Christmas lights analogy if you had to describe what bitwise operators do, because again, all numbers are 32-bit sign integers in code most of the time. In terms of our friend Big O for both these guys, as always, I sing the praises of the bitwise operators being incredible for Big O, and they are here as well. This one has a time and space of 1. That is because it involves a single AND operation and a comparison, both of which are constant time operations. The number of operations doesn't depend on the size of the input. The bigger the number gets, there's nothing extra that has to happen here. Space complexity as well uses a fixed number of variables. Number and number minus 1 doesn't require any additional space that grows with input size. So that is our lovely straight line down here at the bottom. As always, it is incredible for space and time complexity when it comes to bitwise operators, which is why, again, another reason you should probably know at least a couple tricks with them. This one is not the same case. It has a time of, I think, log n is what I determined on this one, and a space of 1 because there's no variable growing here. Growing in space here is when you have one that's actually going down, which is the input number. But the time complexity is log n, which honestly isn't terrible. As you can see, it's the blue one, so it starts at 0 and then it quickly and then level, and it slowly kind of goes upwards, but it's not as efficient as 1, but it's pretty dang good. So it's not terrible. But then again, this wasn't a particularly complex question that required a lot of time and space complexity. But in the non-bitwise version, the reason it's log n and not just 1 is because the function divides the number by 2 in each iteration of the while loop. So the number of iterations required to reduce the number to 1 is proportional to the logarithm base 2 of the number. So again, that's all we have to worry about. Therefore, that's time complexity, right? Bigger n is, we have a logarithmic scale that grows on it because we divide it by 2. So it's not going to be a square root or a linear line, but because we're dividing it by 2 each iteration, the bigger n gets, obviously the longer it'll be in terms of time, but it's not that bad since we're dividing by 2, and it can quickly get down to 1 no matter what. And then in terms of space, the same holds true here as the bitwise implementation. It uses a constant amount of space. It just simply modifies number in place and doesn't use any additional data structures or anything like that to store it here. So, not that bad in terms of time and space for both of these, but this one, again, you're going to be way cooler if you know how to answer this one. And as always, why this stuff is cool, I've gone over the same reasons why they're cool. Game development is going to be a big place where you'll have like bitwise operators. After I cover a few more, or I don't know if I have any more in my back pocket, like simple or beginner level bitwise operation algorithms, I'll talk about the fast inverse squared root, and we're going to break that down because that's a really cool use case of bitwise operators in game development. It is legendary. It has its own Wikipedia article, for goodness sake. In terms of, and don't forget, computers operate, they're binary systems, computer architectures, hardware interaction, all that kind of fun stuff. Knowing how to divide something even by a power of 2 is great to do so. When it comes to like memory alignment, for example, we know that memory is bound in powers of 2, 1024, 2048, right? 64. These numbers you've seen your whole life are base powers of 2. So you know how to align stuff with memories. It can optimize memory allocation and access, leading to some strong performance improvements if you have to deal with anything like that. your common data structures, algorithms, digital signal processing, graphics, network data encoding, encryption, all like your typical suspects when it comes to Bitwise operations and things like that. So this one was a bit shorter by about 10 minutes. Some other Bitwise stuff, but it's a wrap of our Power of Two quest. If you felt that light bulb moment and unraveling that binary puzzle hit us in your head, then hit us with the like button. Subscribe to our channel and hit that bell notification to get more of our videos that come out on the regular. And remember, each line of code you write is a step towards mastery. So I hope all y'all stay curious, keep challenging yourselves, and most importantly, enjoy this journey. So I'll see y'all in my next video, whatever it happens to be.